With this lecture, we continue to consider gastrointestinal physiology, and now we come to digestion in the intestine. The small intestine is a major site for digestion and absorption of food substances. It consists of the three parts, as you remember from anatomy. These three parts are duodenum, jejunum, and ileum. Total length of the small intestine is about 3 meters. Digestion in a small intestine is carried out by 3 digestive juices. First, pancreatic juice, then bile, and finally the own intestinal juice. First, let's recall the anatomy of duodenum, pancreas, and gallbladder with biliary ducts. First, you see here duodenum and major glands. Not all of them are shown in the picture. Pancreas is shown, and you can see pancreatic duct that passes through the whole gland and opens into the duodenum. The liver itself is not shown at this picture. It's located above the screen, but hepatic ducts are shown. They come to join the duct that goes from the gallbladder, the cystic duct. Hepatic ducts together with cystic duct after joining form the common bile duct. This duct goes down to the duodenum and opens as major duodenal papilla. Usually it opens together with pancreatic duct, but sometimes it's open separately. Pancreatic secretion. Let's begin to consider this very important for digestion juice. The total amount of pancreatic juice formed daily is about 1 liter. The pH of the pancreatic juice is between 8.1 to 8.3 on average. Pancreatic juice consists basically of the 2 main parts. One part is enzymes secreted by pancreatic acini. You can see here acinar cells that surround the end of the ducts, and these cells produce enzymes and release into the duct. Then HCO3- ions, as well as the most of simply fluid water, secreted by the ductal cells that simply around the ducts. And as you remember, inside of the generally exocrine gland, pancreatic gland, there are numerous pancreatic islets of Langerhans. These are pieces of the endocrine tissue inside the exocrine gland. And as you remember about their endocrine function, they produce insulin, glucagon, and somatostatin. Let's recall again the pancreatic juice main components. Acinar cells produce enzymes, which are necessary for digestion of all food substances. And ductal cells add another component, which is HCO3- ions, as well as most of fluid, water. HCO3- ions are necessary for neutralizing of the acid content that comes from the stomach, and also to create the necessary pH for enzymes' optimal action. How the HCO3- ions are produced by the ductal cells. Similarly to consideration of H+ secretion by parietal cells, let's consider this mechanism. The ductal cells produce HCO3- ions secrete by chlorine and HCO3- exchanger. But they produce HCO3- ions due to action of the carbonic anhydrase, as usually as we produce H+ ions for gastric juice. Here, this is the pancreatic ductal cells. To the left side, you can see the blood vessel, and to the right side, the lumen of the duct is located. So secretion should go to the right side, to the lumen. And first, it's necessary to produce HCO3- ions by carbonic anhydrase. CO2 production of the cell is not enough in most cases, therefore it's necessary to take some CO2 from blood. And then CO2 with water are combined by carbonic anhydrase action into H2CO3, carbonic acid. which dissociates into H plus and HCO3 minus. But now, in contrast to the gastric secretion, we need not H plus ion but HCO3 minus. And exactly HCO3 minus is transported into the lumen in exchange with chlorine ion. Here it's exchanger, not a pump. And finally, HCO3 minus ions appear inside the duct. Then, H plus ions are removed into blood using exchanger, but exchanger works due to low sodium concentration in the cell, which is maintained due to action of the usual sodium-potassium pump that constantly keeps sodium concentration in the cell at a low level. And now sodium with H plus ions are exchanged. Also, additional amounts of sodium can be attracted between cells due to charge. Negative charge of H2O3 minus attracts more sodium, and as well water goes due to osmotic reasons into the lumen of the duct. And thus we have HCO3 minus bicarbonate ions, sodium ions, and water that produce fluid part of the pancreatic juice. Pancreatic enzymes, most important for digestion of all the types of nutritional substances. And the largest group is the Pancreatic Proteases group. Let's consider all enzymes in regular order, from proteins digestion enzyme, then fats digestion, then carbohydrates digestion, and last class will be for nucleic acid, which do not belong to previous classes. So proteases, as I already said, is the largest groups, and there are many of pancreatic proteases. Let's name all them. Trypsin is the main protease of the pancreatic juice. It's most abundant and most important because it becomes active first. Then chymotrypsin, and the third one, elastase. These three types of enzymes are endopeptidases. It means that they cut peptides that come from the stomach into rather big pieces, making cut somewhere in the middle. Not necessarily perfectly in the middle, just not the ends. And therefore, from larger peptides, we produce progressively smaller and smaller ones due to action of the endopeptidases. There are some more carboxypeptidases. Carboxypeptidases produce cut of the end amino acids from the C end of the protein and from the peptide, and they are exopeptidases. So they produce just a little smaller, negligible smaller peptides and amino acids. All these proteins are released in their inactive state. Inactive. They are called trypsinogen, chymotrypsinogen, proelastase, and procarboxypeptidases. Otherwise, if they are produced in exactly inactive state, they may simply digest the pancreatic gland itself, and they must be activated only when they reach the lumen of the duodenum. First, what is activated first? This is trypsin. Trypsinogen becomes connected to trypsin by the enzyme called enterokinase. If you remember that the Greek name of the intestine is enteron, you may guess that enterokinase is the enzyme produced inside the small intestine. And only when juice reaches the small intestine, trypsinogen can be converted to the trypsin, active trypsin. Active trypsin then converts all the remaining proteolytic proenzymes into their active form. Activation. Let's observe this process of activation. First, in the pancreatic duct we have trypsinogen, and in the duodenum we have enterokinase, and enterokinase converts trypsinogen into trypsin. When first molecules of trypsin are formed, it greatly contributes to activation of the rest trypsinogen. It's the so-called autocatalytic process. But first molecules of trypsin cannot appear without enterokinase. But it's important then when trypsin becomes activated by enterokinase, the rest of trypsinogen becomes very quickly converted to trypsin. And then trypsin easily converts the other enzymes from their inactive form into active. Chymotrypsinogen is converted by trypsin into chymotrypsin. Proelastase is converted by trypsin into elastase, and procarboxypeptidases become converted by trypsin into carboxypeptidases A and B. Lipases. Number 1 is the so-called pancreatic lipase, which hydrolyzes neutral fat into fatty acids and monoglycerides. This is very powerful enzyme that produces split of fats very quickly. Just it needs the high surface area of fats. It can digest lipids only in the emulsified state, which is achieved due to bile. When lipids are in larger particles, even these particles can be, for us, rather small. For lipase, they are too large, and it can work only on the surface. And with larger size, the surface is negligible relatively to the volume of the total droplet of the lipid. And smallest droplets can be formed only due to bile. You know, lipids tend to join the droplets, making progressively larger and larger ones. And even shaking or any movements of the intestines can produce smaller particles, but without bile they cannot be stable. These particles again join each other and form again larger and larger. And only due to bile the droplets, smallest droplets of lipids can be formed, and they do not join each other, and this is the so-called emulsion. Emulsified state of lipids is required for action of pancreatic lipase. And also lipase requires specific coenzyme, colipase. Colipase enables the lipase to be attached to the surface of the lipid droplet, and then lipase starts to operate. Numerous molecules of pancreatic lipase easily digest lipids which become emulsified, and of course if colipase is present. The other lipases are cholesterol esterase, which splits esters of cholesterol, and another one, phospholipase A2, that splits fatty acids from phospholipids. Phospholipase A2 is the only one enzyme not belonging to proteases that also is secreted in inactive state and requires activation as usual by trypsin. It's initially secreted as prophospholipase, and under trypsin action becomes converted to phospholipase A2. And it's logically can be easily explained why it requires to be not active initially, because phospholipids are the main components of the membranes, and if membranes will be digested, it would result in digestion of all the cells, activation of all the rest enzymes by lysosomal enzymes, and so it will result in autodigestion of the gland. So all proteases are secreted in the inactive state, and as well as one more enzyme, phospholipase A2. All the rest enzymes are produced already active, but they cannot actively digest anything because normally lipids are not accessible for the enzymes. The other lipids and also carbohydrates are not accessible while juice passes through the ducts. Carbohydrases. But first let's consider how hydrolysis occurs of fats by pancreatic lipase. It was studied, I think, in biochemistry course, but let's recall again. This is classical triglycerol, triacylglycerol. You can see the glycerine ring and also the three chains of fatty acids. Under action of pancreatic lipase, the hydrolysis reaction occurs. Hydrolysis occurs using molecules of water. And look, two fatty acid chains are removed, these two, the first position and the third position, and only middle one remains at place, so monoglyceride will be formed. Then two H atoms are added to the glycerol, monoglycerol, so that OH groups are formed. And the other OH groups are added to the fatty acid chains. So you can see a result from the, for example, given here tristearine, you can see formation of monoglyceride with present fatty acid chain in the second position, so it's 2-monoglyceride, and stearic acid. You see two molecules of stearic acids are formed. So 1 monoglyceride, 1 molecule of 2-monoglyceride with position of fatty acid chain in the second place, and stearic acid 2 molecules. This is classical hydrolysis of fat by pancreatic lipase. Carbohydrases, the enzymes that split carbohydrates. And the main is alpha amylase, well known from the saliva. But here alpha amylase has much longer time for action, and it actively easily splits starch and glycogen into smaller pieces. And this includes formation of the number of substances of different size. But first, how alpha amylase operates. It hydrolyzes linkages that are known from biochemistry and bioorganic chemistry as alpha 1.4 glycoside. These linkages shown here with an atom of oxygen in between. And these complex carbohydrates such as starch and glycogen are converted to larger branched polysaccharides such as alpha dextrins, then maltotriose trisaccharide, and maltose disaccharide. The last class is nucleases, and as we have only 2 nucleic acids, DNA and RNA, so it will be DNase and RNase, 2 enzymes. All the enzymes listed in this slide are produced in the active state. There is no danger because these enzymes do not have substrates for digestion while the juice passes through the duct, and only inside the lumen of the small intestine these enzymes can start their operation. Regulation of pancreatic secretion includes, as usual, stimulation by parasympathetic system through neurotransmitter acetylcholine. And this is initial stimulation that occurs by stimulation of conditioned reflexes even before food enters the body, and unconditioned reflexes beginning from passing the pieces of food into an oral cavity. But this secretion is just preliminary, just a little amount of enzymes is produced and is released into the ducts, but movement, flow does not appear yet. Then cholecystokinin, this is very powerful stimulator of the pancreatic secretion. Cholecystokinin is secreted in the small intestine, so this substance appears after beginning of gastric emptying of chyme into the small intestine. And cholecystokinin stimulates acinar cells, therefore it increases the secretion of enzymes. Cholecystokinin is secreted by the duodenum and jejunum eye cells in response to small peptides, amino acids, and fatty acids in the intestinal lumen. So main stimulators of the cholecystokinin secretion are products of digestion of proteins and fats. These substances stimulate eye cells, and cholecystokinin is released into blood. Then, with blood, it passes through the whole circle and finally through arteries comes back to the small intestine and stimulates pancreatic acinar cells so that enzymes start to be secreted in large amount. Secretin, it's another important substance that increases pancreatic secretion and greatly contributes to higher volume and higher amount of bicarbonate ions because secretin acts on the pancreatic ductal cells, and therefore HCO3- ion secretion greatly increases. Secretin is produced by S cells in the duodenum, and stimulus number 1 for secretin is H+ ions coming from the stomach. In response to H+ ions, secretin generally increases secretion of neutralizing H+ HCO3 minus ions, and not only in pancreatic juice but also in the bile and even in intestinal juice. But number one for neutralizing of the acid content from stomach is HCO3 minus ions from pancreatic juice, which are produced under stimulation by secretin. So let's observe it again. Vagus stimulates release of enzymes into acidity, just a small amount relatively, and it occurs even before food enters the duodenum. It starts from the beginning of eating, and from oral cavity receptors, reflexes begin that stimulate vagus, and from gastric receptors also this stimulation occurs. First impulses are sent to vagus nuclei and then back through vagus to the pancreatic cells, and secretion increases, but not greatly. Acid from the stomach releases secretin from the walls of duodenum, and fats and amino acids produce release of cholecystokinin. Now it's the intestinal phase for pancreatic secretion, when most of the juice is secreted, and a lot of fluid washes the enzymes through ducts, and flow of the pancreatic juice greatly increases, and it is released into the intestinal lumen. Secretin and cholecystokinin produce its effect not directly but passing through bloodstream, and finally copious secretion of pancreatic fluid and bicarbonate stimulated by secretin occurs, while cholecystokinin causes secretion of enzymes. Let's recall again. Cholecystokinin is a stimulating factor for a greater amount of enzymes in the pancreatic juice, while the secretin stimulates bicarbonate ions secretion as well as the generally fluid, and contributes to great amount of pancreatic juice. Now let's move to the bile secretion. Bile secretion occurs regularly and constantly by the liver, but when bile is not necessary at the moment, it can be stored in the gallbladder. Total amount of bile produced daily is about 1 liter, similarly to pancreatic juice. The pH of bile is approximately 7.8. The main components of bile salts, which are salts, usually sodium salts of the bile acids. Then bilirubin, bile pigment. As you remember, it is present in the bile only for one purpose, to get rid of this, to excrete it out of the body. Then cholesterol, phospholipids, mainly lecithin, and ions, numerous ions, and water. Among ions we can mention, of course, the usual sodium, chlorine, and so on, but it's important that here we have also HCO3 minus ions. And their secretion is also, to a lesser extent, stimulated by secretin. Hepatic ducts, let's recall cystic duct, and they form a common bile duct together. And finally, bile is released into the duodenum, but release is controlled by the sphincter, which is located in the area of the entry. This is so-called OD sphincter. Only when it's relaxed, bile can be released into the intestine. Functions of the bile. Now, first, emulsification of fats for their further digestion by pancreatic lipase. Then, solubilization of fat digestion products. When fat is already digested by lipase, it still remains fat, not dissolved in the fluid. Therefore, it's necessary to keep it still solubilized. And due to formation of the so-called micelles, bile performs this function of solubilization. Then excretion of bilirubin, it's an excretory function. Also, certain amount of excessive cholesterol can be released together with bile. Then stimulation of intestinal secretion and motility is also important bile function. Then participation in acid neutralizing because of presence of HCO3 minus ions in the bile. Actually, most important neutralizing acid action is due to pancreatic juice, but certain amount of HCO3 minus also contributes to this in the bile. And bacterial static action. It's not bactericidal, not killing bacteria, but preventing the growth of bacteria, bacteriostatic action. These are all functions of the bile. Let's observe in more details. Emulsification of fats, how it occurs. Emulsification of fats requires enough molecules of the bile salts because their number must be very high. First, look, bile salts are submerged with their hydrophobic tails into fat droplet, and hydrophilic polar heads are outside. Therefore, each little piece of fat, little droplet of fat, is surrounded by bile salts molecules with their polar hydrophilic heads out. So the total droplet becomes soluble and surrounded by water molecules easily. And when such two droplets meet each other, they do not join, do not form one larger molecules. And with regular shaking, which is produced by movements of the intestines, gradually the fats become smaller and smaller and smaller progressively without forming back the separation of water and fat. This is very important emulsification function. So bile salts, they have, as many other surface active substances, have hydrophilic head and hydrophobic tails. Hydrophobic tails are dissolved in lipids, therefore they can be placed into the fat droplet. And don't forget that on the surface of the small lipid droplets, lipase is fixed with the help of colipase. And then lipase can easily digest fat when fat droplets are very, very little. So, role of bile in digestion and absorption of fat. Here you can see the duodenum and generally small intestine located as one line. Also, you can observe the fats that come from the stomach with the chyme and opening of the common bile duct. From liver and gallbladder, bile is released, and rather small, even initially, fat droplets must be broken into smallest droplets, and bile helps to do it. So first stage is emulsification of fats. This is necessary condition for proper digestion of fats by lipase. Then lipase acts and hydrolyzes the triacylglycerols into free fatty acids and monoglycerides. Hydrolysis. And after hydrolysis, bile still is necessary because it produces solubilization of fat digestion products into micelles. And these micelles contain, again, the covering with the molecules of the bile salts with their polar heads out, and inside there are fatty acids, monoglycerides, some cholesterol molecules, and all this is kept as dissolved in the content of the lumen. And then these micelles can come close to the brush border of intestines, and the fatty acids and monoglycerides easily diffuse through enterocyte membranes, and that's how they become absorbed. Let's recall what is the primary and secondary bile acids. Perhaps you studied in biochemistry, but let's recall generally the source of production of bile acids is the cholesterol, and liver makes these molecules out of cholesterol. And first, bile acids are formed as the primary bile acid. There are two of them, cholic acid and chenodeoxycholic acid. They are primary. And exactly like this, they are released in a state with sodium, as sodium salts. They are released into intestine. But intestinal bacteria change the bile acids, primary ones, into the secondary bile acids. And as a result, deoxycholic acid and litocholic acids are formed. Enter hepatic circulation of bile salts. It's important that the bile salts are used many times after even one meal that contains enough fat, because the total amount of bile acid is not enough to produce full digestion of all the fat present in the daily food. Recycling of bile salts occurs between liver and intestine constantly, and the same portion of the bile salts can be used up to 3, 4, 5 times for digestion of one and the same meal that contains fat. Here you see the general route of bile acids. And about 95% of all bile salts we can absorb back. The site of absorption is the distal part of the ileum. Ileum itself is the last portion of the small intestine, and the most distal portion exactly contains cells that specifically are able to absorb the bile acids. And as they are absorbed and go into portal blood, so the portal vein then comes back to the liver and bile acids are taken again. The certain amount is lost, and the liver produces more of the bile acids. So first you see liver forms the bile acids, releases into intestine. Then the bile acids, salts of bile acids pass through the small intestine and help to perform the function and help to digest fats and help to absorb these products of fat digestion, and they are not absorbed until they reach the distal ileum, and only in the distal ileum they become absorbed into blood. This blood passes through portal vein and comes back to the liver, where liver cells take the bile salts again and reuse them. And so thus we have constant reuse of the bile salts, and we managed to absorb back about 95% of bile salts, while about 5% usually are lost. 5 to 6%. Excretion of bilirubin, one more important function. Let's recall the way how bilirubin is formed and released from the body. Each time when old red cells are destroyed, the heme taken from hemoglobin by macrophages, iron is extracted from this heme and reused again through transferring it directed to the storage in the liver or directly to the bone marrow where new red cells are formed, while the remaining portion of heme becomes converted in a few stages into bilirubin, and macrophages release this free bilirubin into blood. Bilirubin is not dissolved in water, therefore it cannot be dissolved in blood, and it's transported in blood attached to albumins. The transport function is performed in this. Then bilirubin reaches the liver cells, and the liver cells take bilirubin molecules and produce conjugation with glucuronic acid. As a result, bilirubin becomes a little bit more water soluble, and it is excreted into bile. Liver cells take it from blood and pass to the other side where bile canaliculi pass, and so the bilirubin appears in bile. With bile, bilirubin is released into the small intestine, into duodenum, and passes through the intestine. Bacterial flora hydrolyzes the bilirubin, and so let's observe this. Excretion in bile, then hydrolysis by bacterial flora. Bilirubin is converted to urobilinogen. Urobilinogen is water-soluble substance. Therefore, partially it becomes absorbed into blood. And then, as water-soluble substance, it easily becomes excreted in urine. And remaining urobilinogen, or it becomes converted to stercobilin, is excreted in feces. So this is a way for us to get rid of bilirubin, which is toxic in higher concentrations. In normal amount, it doesn't produce any harm, but when it increases higher and higher, it may be toxic for nervous system and many other organs. Conjugation of bilirubin. It's also known from biochemistry, but let's recall. lipid-soluble bilirubin transported in blood as albumin-bound bilirubin. When blood passes through the liver, the bilirubin is taken from albumin and conjugated. See, as a result, bilirubin glucuronide is formed and released to the other side of cells, hepatic cells, into bile. Excretion of urobilinogen. Let's observe. Bilirubin is converted by bacteria into urobilinogen, and this substance partially is excreted through gastrointestinal tract and partially is absorbed back to blood and then is released by kidney in urine. This is final way of excretion of bilirubin. Final ways. Regulation of bile secretion. Primary bile secretion is regulated by the cholecystokinin hormone that is released from eye cells. So, mainly bile is produced when chyme already appears in the duodenum, where eye cells are present, and when this chyme contains enough fat. Cholecystokinin has direct effect on the gallbladder. It produces its contraction, and at the same time there should be relaxation of the sphincter Oddi, and so it results in release of bile into intestine. Vagal stimulation also causes release of bile from gallbladder, but much weaker. Secretin contributes to higher amount of bicarbonate ions in bile. So these are main factors. Let's see this on the picture. Stimuli for bile secretion and gallbladder emptying with release of bile into intestines. First, bile stored and concentrated in the gallbladder, usually up to 5 times, but it can be concentrated up to 15 or sometimes even more times. Again, bile is produced constantly, but it is required not constantly, and temporarily it can be stored in the gallbladder. And gallbladder mucosa is able to absorb water and gradually to concentrate the content so that the new portions can be placed into the gallbladder. Then, vagal stimulation causes weak contraction of gallbladder. So, before food entry into the duodenum, the bile can be released only in a little amount. Cholecystokinin, main stimulating factor, which comes through blood, produces contraction of the gallbladder and relaxation of sphincter of Oddi. Then secretin stimulates ductal secretion in the liver so that more bicarbonate ions appear in the liver, in the bile produced by the liver. And the main stimulus for secretin is H plus ion, then H plus ions coming from the stomach. Therefore, the more acid appears in the duodenum, the more secretin is produced, and bicarbonate ion secretion increases in pancreatic juice, in bile, and also even in intestinal secretion. And bile acids stimulate secretion, bile acids themselves. So here we have something like positive feedback. The more bile is released into intestine, the more bile acids become absorbed back, and with blood, with portal vein blood, they come back to the liver, and more blood brings more bile acids, and so liver produces again more bile. So the higher is use of the bile, the more bile salts come back, and the more new bile it is produced. This is a positive feedback. Now let's observe some portion of pathology. Formation of the gallstones. Causes of gallstone. Too much absorption of water from bile. You see, it can happen when bile stays for very long time in the gallbladder. It's cholestasis. So it will show that great intervals between meal are not very good. Then, too much absorption of bile acids from bile, too much cholesterol in bile, inflammation of epithelium, the last possible reason. Too much cholesterol also can be a result of excessive absorption of fluid, so that concentration of components becomes very high. And inflammatory processes greatly contribute to the formation of the stones. And what may happen in this case? Initially, there are only crystals, like for example cholesterol crystals or bile acid crystals are formed. But time after time, gradually they become layer by layer larger and larger, and finally they form real stones. And here is an X-ray that shows the gallbladder filled, half filled, or more than half filled with the gallstones. And there is one more danger in this case, because when the gallbladder contracts, it can release the gallstone into the duct, and it can be large enough to block the duct itself. But in most cases, the gallstones block not the duct in the middle, but the duct in the area where it enters the duodenum. Look at this. It comes to the sphincter odi, and here it can block the entry into the intestines. And so this produces serious problem, absence of bile release into the intestine. Bile duct obstruction. Let's observe what will be the result. Bile duct obstruction. If bile does not enter the intestines, the consequences can be easily deduced logically from the main bile functions. First function, emulsification of fats for the digestion by pancreatic lipase. No bile, no emulsification. So the fats will be not digested and thus are excreted in the unchanged state. So it's so-called fatty stool or steatorrhea from Greek term. Then, excretion of bilirubin, its important function, cannot be performed without release into intestines. So, excretion of bilirubin not performed results in great increase of blood bilirubin level. When it exceeds more than twice the upper normal limit, bilirubin as a pigment makes coloring, yellow coloring of the skin and mucous membranes, the so-called jaundice. Then, stimulation of intestinal secretion and motility. Also, there will be no stimulation of secretion and motility, and so there will be great decrease of both intestinal secretion and motor function of the intestine, atony of intestines. So, for toxicity of bilirubin, I think I don't need to remind you, because we consider this in blood. High level of bilirubin can be dangerous for nervous cells, but especially, usually it's most dangerous for young children. But for adults, it's also toxic and produces its toxic effects on many organs and systems. So all this is called obstructive jaundice or mechanical jaundice. Intestinal juice. It's formed about 1,800 milliliters daily, and pH of this juice is between 7.5 and 8 units. Intestinal juice also contains numerous enzymes, but generally they need not to digest large food substances, large molecules, because by the pancreatic juice and even preliminary digestion by pepsin in the stomach, also we have smaller particles to be digested. And therefore, there is number one enzyme for trypsin activation, enterokinase. Then enzymes for proteins digestion usually are dipeptidases and generally peptidases. Smaller peptides are digested by intestinal enzymes. Tripeptides, dipeptides. Tripeptides and dipeptides are already split using the intestinal juice enzymes, which are located in the brush border on the surface of enterocytes, in contrast to luminal peptidases of the luminal proteases of pancreatic juice that operate inside the lumen. Then enteric lipase. It's much less important for digestion because the pancreatic lipase is so powerful that it digests almost everything. Just little remnants, little amount of lipids can be digested by enteric lipase. Then set of brush border carbohydrases. Here is the most numerous type of enzymes. Alpha dextrinase cleaves against the alpha 1.4 bonds, producing free glucose. Then maltase splits maltose and maltotriose to glucose, and lactase hydrolyzes lactose into glucose and galactose. So you see, products of digestion by alpha amylase are finally digested by intestinal carbohydrases, brush border carbohydrases. And sucrase splits sucrose into glucose and fructose. Now let's observe how carbohydrates digestion is completed. First, in the lumen of the intestine, the starch is hydrolyzed by amylase into alpha-dextrins, maltotriose, maltose. And also the food can contain the other ones. And then membrane digestion occurs by alpha-dextrinase, maltase, sucrase, and number of others. And final products are formed such as glucose, galactose, and fructose. So, luminal digestion, it's performed predominantly by the pancreatic juice enzymes, which operate inside the lumen and produce from larger particles smaller ones, smaller molecules. But final digestion occurs due to membrane digestion by enzymes of the brush border that belong to the intestinal juice. And so there should be a sequence of events. First, luminal digestion makes smaller and smaller substances, and then final conversion of smallest substances into the final products occurs by membrane digestion. Glucose, galactose, and fructose are main products of carbohydrates digestion. And exactly these three monosaccharides can be absorbed from intestine. Complete proteins digestion occurs beginning in the stomach. Proteins in the stomach become first denaturated by hydrochloric acid, and then pepsin converts them into peptides. Sometimes larger peptides, sometimes smaller, but generally peptides. Then these peptides in the chyme are supplied into small intestine, where trypsin, chymotrypsin, and elastase and carboxypeptidases operate in the lumen of the small intestine and convert peptides into amino acids, mostly due to carboxypeptidases, and into dipeptides and tripeptides due to action of the other enzymes. And larger peptides also can be formed, oligopeptides, which finally, by brush border peptidases, are converted to final, again, amino acids mostly, but also dipeptides and tripeptides. And these are final products of protein digestion, because mostly they are amino acids, but also dipeptides and tripeptides also can be absorbed into enterocytes. So they are ready for absorption. Absorption of protein digestion products. From lumen, the products should enter the epithelial cells of the small intestine. And amino acids are absorbed by sodium-dependent secondary active cotransport. Cotransport here means that direction is the same for both sodium and amino acids. Why it's secondary active? Because itself here, carrier protein, doesn't use energy. But all is based on a sodium gradient, which is constantly maintained by a regular sodium-potassium pump using energy, and this pump is located in the opposite side of the cell, not luminal, but basolateral. So sodium-dependent secondary active transport transfers amino acids together with sodium. Protein carrier binds both sodium ion and amino acid. There are specific transporters for different amino acids. And then amino acid is transported through membrane from the lumen. Then amino acid is transported by another protein carrier outside into interstitial space and finally into blood by carrier proteins. Dipeptides and tripeptides also are transported into into cells first, and then partially they can come to blood themselves, but mostly they are digested inside the cells into amino acids. And then these amino acids are transported by carrier proteins into blood. So transportation of proteins, digestion products occurs by secondary active transport, sodium dependent. Absorption of fat digestion products. It's more complex way, but as fats are lipid-soluble substances that can pass into cells by simple passive diffusion. Let's recall triglycerides. Due to action of the lipase in the presence of bile salts, which perform smallest particles, emulsion of fats, converted to fatty acids and monoglycerides. And then these substances, by passive diffusion, simply pass into the cells, where the triglycerides are formed again, but the different are our own triglycerides. Resynthesis of triglycerides occurs inside the cell in the endoplasmic reticulum. And these triglycerides are used to form chylomicrons. With apoproteins addition, they form chylomicrons, and they are finally transported into lymph. This is the only type of products of digestion that is transported not by blood but by lymph. Fat digestion products absorbed into lymph vessels, and then they come through thoracic duct. Only then they come into blood. But first they absorbed into lymph in the microvilli, in the intestinal brush border. Absorption of carbohydrates digestion products. Again, to the left side we have the lumen, and to the right side will be blood. And glucose, galactose, these two monosaccharides are absorbed, again together with sodium, carried by specific glucose transporters type 1. And again, as you can see, this is a sodium-dependent secondary active transport. And only one, fructose, is transported by the facilitated diffusion. Somehow it uses another transporter which is not related to sodium. So it decreases the amount of this monosaccharide absorption as compared to glucose and galactose, because sodium is greatly contributing to this transportation. So all these are carrier proteins, transporters. And the other type of glucose transporters, GLUT2, is used to transport all these three monosaccharides. And sodium constantly is pumped out of the cell by a regular sodium-potassium pump. And only due to low concentration of sodium, carrier proteins can move sodium inside the cell down the gradient. And sodium is transported into the cell together with glucose. Out of cell, glucose 2 transporters transport glucose, galactose, and fructose. Notice all these transporters are insulin independent, not related to insulin. Glucose, galactose, and fructose all are transported into blood. So mostly, not all of them, but mostly the carbohydrates, simple carbohydrates, monosaccharides, are transported by secondary active transport. And the last portion, colon, is the place of the smallest absorption. Colon does not have digestive enzymes. There is no enterokinase, and there occurs only processes of reabsorption of sodium, chlorine, and water, which follows sodium and chlorine. And at the same time, there is a secretion of potassium and HCO3 minus ions. So, reabsorption of sodium occurs by regular pump, sodium-potassium pump. Water follows sodium due to osmotic reasons, as well as chlorine is exchanged with HCO3 minus ion. So generally all these processes are here. Water reabsorption is dependent on sodium reabsorption. And also, if you remember, large intestine is a place of living of the normal intestinal bacteria. And these bacteria produce for us necessary vitamins. K, B1, B2, B6, and so on. Group B vitamins. Not many of them, but certain amount is produced. And that's the whole consideration of digestion in the intestine.